The data is falling. The data is falling. Okay, maybe numbers aren't exactly falling from the sky, but the sheer amount of data coming at us every day may be a bit overwhelming at times. One thing that can be agreed upon in this virtual deluge of data is that we need to deal with our data more efficiently and a whole lot faster. Where is that umbrella anyway? Hi, I'm Amelia Dalton, host of Chalk Talk. Data acceleration is crucial to today's fast moving, data intensive world. In today's Chalk Talk, Tom Spencer from Achronix and I take a closer look at the technologies pushing data acceleration today and how we can accelerate our data with the performance, power efficiency, and workload flexibility we need with the help of Achronix Speedster 7T FPGAs, SpeedCore E FPGA IP, and Vector Path Accelerator cards. And before we get started, don't forget to click that link. There you can find even more information about this topic from Achronix. Hi, Tom. Thank you so much for joining me today.
Hey, Amelia, how are you?
I'm great. How are you?
It's a good day today.
Excellent.
So today we're going to talk about this explosion of data worldwide. A lot of people refer to the digital transformation. This has been going on for a number of years. We're going to talk about the technologies that are involved with this, technologies that are going to address it. One of those areas is going to be around what we call data accelerators. This is going to allow us to process data faster and more efficiently. And then we're going to look at the Achronix FPGA technology and how that technology addresses this market space.
Okay, so Tom, what are some of the use cases driving this tremendous data growth?
Let's start with big data. Most technologists would agree that approximately 80% of all data that's generated worldwide is what they call unstructured data. This would be things like video, audio, could be emails. We need to take compute resources, structure that data, then we can actually run things like analytics. Analytics are going to run algorithms that look for anomalies, look for trends, look for corner cases. That gives us information to make business decisions. It could give us information to replace equipment when it's failing. We also have things like sensor data. A great example of that is ADAS, or driver assist technology. Everyone knows about autonomous vehicles. Autonomous vehicles require lots of data. This could be acoustic data, LiDAR, radar, could be video, and they take that information and then they process it, and that allows the car to function as it does. You could also look at sensor data like pressure, temperature, and speed in Industry 4.0. Here you've got robotics where the sensor data is coming in, you got to process it quickly and then make decisions. The IT infrastructure, this is in every market, whether it's automotive, medical, telecom, enterprise, they're all moving to digital. They've been moving to digital, and they'll use these technologies in big data and analytics. Client information. So you've got patient records in the medical industry, banking information and financial services, insurance information, and the big one is your digital footprint. All of us have these smartphones that we walk around with, and you've seen all of these examples of where the data is being collected at a constant rate of where you're going, what you're doing, what you're looking at, what you're searching. They use this to sell to advertisers. They use this to make product decisions and do product research. That's all critical information. And then finally, content delivery. Everybody's streaming these days. You've got in the medical industry, digital imaging and records. And another area in content delivery, and this is combining some of the technologies that we'll talk about, is you look at things like YouTube and Netflix. They're constantly recommending different content for you to look at, and they're not doing that in a vacuum. They're doing that based on your digital footprint.
That makes sense. So we agree that data is growing exponentially, and we can definitely see these use cases in the digital world. But Tom, can you talk about some of the technologies that are behind these use cases?
Sure. Let's start with probably the hottest topic in the industry right now, which is artificial intelligence. And machine learning, ML, is a subset of artificial intelligence. And then you have deep neural networks. And this technology can be used for things like object detection in the automotive industry. So we have the autonomous vehicles. You're capturing all this data, and then they're running these algorithms, and they're looking for certain information. In the financial services industry, they do things like risk mitigation, where they're placing pretty heavy bets on different securities, different trades, and they run risk mitigation algorithms to try to mitigate any downside in some of the investments that they're making. You've got efficiencies. So if you look at Industry 4.0, largely robotics, lots of Internet of Things. So you've got all these data collection devices, and then we're processing the information. What are we looking for? We're looking for how efficiently a machine is running. We're looking for potential defects in the machines or the robotics. The machine learning algorithms can actually find a better way to use the equipment that's out there. And then you have things like database analytics. This can be used in the enterprise. So all this data that's coming in is stored in these large databases. And to run the analytics, a lot of the artificial intelligence or machine learning algorithms are being run to automate decisions. If you've ever been booking a trip on Expedia, and next thing you know, you're going to Aruba, you're getting on your Facebook page or in your Google email, you're seeing advertisements around Aruba. This is database analytics. So AI and ML is a big, big component. If we look at computational storage is all about taking compute and co-locating it with the storage. So now I can do pre-processing. I can actually run database analytics in my computational storage as an example. And then there are storage acceleration technologies like deduplication, RAID, and other technologies that you can incorporate in computational storage. Then if we look at 5G, 5G is 10 to 100 times faster, depending on the deployment model, than 4G is. And you can have as many as 500 times more users per hub than you did with 4G. The technology is also extremely lower in latency. And what you'll see later is we'll talk about the edge compute. By moving a lot of the core data center applications out to the edge, we'll be able to process the information faster, going from maybe 100 milliseconds down to single-digit microseconds. That drives a lot of applications around automotive, like autonomous vehicles, in the medical world, real-time video, gaming. Lots of different industries and applications are going to require very low latency. If we look at network acceleration, I need to move data faster with lower latency, and the key thing being deterministic. And technologies such as software-defined networking, network function virtualization, they create these big flat networks, which allows data to move faster geographically and offer extreme number of unique IDs so that you can isolate different information, upwards of 65 million unique IDs. And then edge compute, as we talked about, it's moving that data center application out to the edge.
So, Tom, you've mentioned that data keeps growing exponentially. Just how much data are we talking about here, and how fast is it growing?
Well, let's look at the amount of data that's generated every day. So this was taken from, I believe, 2018 or 19. 294 billion emails per day, 230 million tweets, over a billion Google searches, and growing quickly. Smartphones create data, taking video, taking pictures. If you look at the storage capacity, this is mind-blowing. 1956, if you had a single drive on a computer, you could store 2 photos. Today, you could store 12 million photos. I was thinking back to when, I don't know if you remember PCM-CIA cards. These were the first flash storage media, and they were about the size of a credit card, but a lot thicker. And you'd plug it into your laptop. And I remember it came with a massive 32 megabytes. Now we're looking at 12 million photos. Instead of 32 megabytes on a card, we now have a terabyte flash storage on your laptop. It's a tremendous ability to store data. And then look at the digital data worldwide that's being created. As recent as 2018, 4.4 zettabytes. 2 years later, we're at 44 zettabytes, and the projections out to 2025 are 175 zettabytes. What are we going to do with all this data? How are we going to process it?
Okay, so Tom, you've mentioned accelerating data multiple times. What exactly does that mean?
So we get all this data coming in, and we need to process it. And we'll look at a traditional model, but really what it is, it's the ability to bring the data in, analyze it, process it. You might compress it, you might convert it, you might need to organize it, going from unstructured data to structured data. And so with the concept of data acceleration comes data accelerators. And in this presentation, what we're talking about are silicon solutions that are acceleration devices. And I've grouped them into a couple categories. So an ASIC would be a predetermined set of functions, but they're not changeable. A GPU, as you know, for quite some time, graphic processing units have been used for artificial intelligence and machine learning, training and inferencing. And then you have FPGAs, which is similar to an ASIC functionality wise, except that it's 100% programmable. So an FPGA can take on any personality you want it to.
Okay, so Tom, how would you compare and contrast these three different data accelerators?
We like to look at performance, efficiency, and flexibility. So if I create bookends, a CPU is going to have the worst efficiency, but it's going to have the most flexibility. It can be absolutely anything you want it to be. You just take software, you put it on the CPU, but it's not the most efficient model. On the complete other side of the bookend is the ASIC. The ASIC is a predetermined set of functions that are designed into a chip, and that's the only thing that chip can do. And if you look at the way the industry has gone, and this goes back probably almost 10 years, and it really took major effect that the cloud infrastructure hyperscalers created an environment where they put in simple servers and they made them software defined. I can put a personality on that machine. It can be whatever I want it to be. Whereas in telecommunications, a lot of infrastructure was built with purpose-built appliances. So once that machine went out there, it only had one function. ASIC is very similar in this analogy. It has one function. So those are your bookends. Now as you come into the middle, you've got graphic processing units, which again found a second home in artificial intelligence and machine learning. And why? They're good at parallel processing a lot of data and doing it really fast. But then if you look at the need for data acceleration, it doesn't just stop with AI and ML. There's so many other use cases for acceleration. That's where an FPGA has the benefit of super fast logic. In the silicon industry, we always say that you can do things faster in gates than you can do in CPU cycles, and that's a true statement. It just moves faster. So with FPGAs, I get the benefit of what's done in gates, and it's 100% flexible. So from a performance perspective, power efficiency perspective, and a workload flexibility, the FPGA is a great solution when you need flexibility.
Okay, so now that we have a data accelerator, where and how does this change more traditional solutions?
So go back to the early days of cloud infrastructure. And what we would do is we take a bunch of servers, a bunch of 1U, 2U servers, and stack them up. And as the data increases and the workload increases, we just throw more servers at the problem. Well, let's look at a server. A typical server can run 300 to 400 watts, could be higher depending if it's a 4U server or 4-socket server. Cost could be anywhere from a $5,000 to $10,000 server. The latency is extreme, up to 10x higher, and it's very indeterministic. When I talk about determinism, it says, I need this piece of data, I need it analyzed. So I send a request in. That request is going to go into the server. Now, the server is working on lots of things. The CPU is working on lots of applications simultaneously. You're going to get into some type of round robin servicing of your request. So you can't really tell when you're going to get the information back from the server. That's not how it works with data accelerators. What data accelerators do is they take the data and they do some type of pre-processing on it, they do some type of lookup on it, and they can accelerate that function. So what we're doing is we're saving the CPU to do real application work, revenue generating work, whereas the data accelerators are going to take all the network processing, the AI inferencing, the ML inferencing, and they're going to do that work for the CPU. So now I need fewer CPUs. And when we do that, we have lower latency, we have a better power, cost, real estate, and we increase the performance overall.
So, Tom, are data accelerators used everywhere?
Everywhere in the networks. So if we go back to the hyperscale cloud data centers using data acceleration, well, there's a whole other dynamic happening now where edge compute is a real thing now. And what we're doing is we're saying, let's not centralize all of the workload applications into a core data center. Let's take some of those applications and move them out to the edge. Why are we doing that? We have applications that need much lower latencies, and there's just so much data, it doesn't make sense efficiency-wise to be pushing all that data through a network all the way to the core data center, all the way back out to the edge. So now it's getting distributed. Some of the technology enablers, so 5G we talked about, much faster, much lower latency, Internet of Things generating data. We have software-defined networking and network function virtualization. And then there's multi-access edge compute. Multi-access edge compute used to be referred to as mobile edge compute, but now multi-access edge compute doesn't just limit it to mobile infrastructure. It's any infrastructure out on the edge. And this is kind of the starting point of the edge of your network. And here's what they're doing. If you look at some of the locations, you could actually have servers sitting in a shopping mall, in a small business. It could be at a gas station or a strip mall. And that's where they're starting to put these things. So what does that mean? If you look at the requirements, power is going to be a big deal because it's going to be in a smaller form factor. It's going to be in a remote location. Security is going to be important. I'm now taking much more data and I'm way outside of a core data center. So hackers and others could get in. And all of these applications are low latency and high bandwidth. If you look at the edge network application example, there's so many different examples. I said earlier, because there's so much data being created, that data accelerator market is on this big rise. So a lot of analysts, including here on this page, say that the CAGR rate can be as high as 41% over the next 5 years.
So, Tom, can you give me an example or two of how data accelerators are used from an implementation perspective?
So we talked about AI and ML quite a bit, and that's been around for some time. So those are a given. When we talk about computational storage and networking, I did touch on a few of these, but let's start with networking. We mentioned the SDN and NFV, but packet capture. So I capture packets. I might run an algorithm. It could be an ML algorithm on the packets, and I'm looking for particular patterns or trends. I might be looking for timing information, or I might be looking for security information. So this could be some type of a firewall appliance connected to my networking. The telemetry part would be used for the timing as another example. So those are examples of networking. On the computational storage side, it could be something as easy as compression or running the analytic. So these are different areas where data accelerators can be used. And as you can see, if you look at the networking and the computational storage, there are so many other use cases for data accelerators over and beyond AI and ML.
That makes sense. So, Tom, can we talk some more about who Achronix is and how your technology addresses these requirements?
Sure. So Achronix develops FPGA-based data acceleration products. This is for compute-intensive infrastructure applications. It's AI ML, it's networking acceleration, storage acceleration, and we hit all these markets that we talk about. What we have is we have a unique portfolio of discrete FPGAs, but we also have embedded FPGA intellectual property. And we'll talk a little bit about why that's significant in the subsequent slides. So let's look at some of the solutions that Achronix offers. Our premier platform today is the Speedster 7T FPGA chip. This is the fastest FPGA in the industry. So that is led by a foundation of what we call a two-dimensional network on chip, or 2D NOC, that's running greater than 20 terabits per second. We can support up to 400 gigabit Ethernet, PCI Express Gen 5. For the memory interfaces, we have your traditional DDR4, DDR5, but we also have GDDR6. This is much higher speed. And then we've done some optimization on our DSP engines for machine learning, and those optimizations, those blocks in our device, we call machine learning processors. Next on the list is SpeedCore. SpeedCore is the embedded FPGA, or the intellectual property that I referenced earlier. That is taking all of the technology that we have in Speedster 7T and making it available as intellectual property. We support this today on various libraries from TSMC and can also port it into other foundries as well. And then finally, we have the vector path accelerator cards. That's taking the Speedster 7T, putting that on a PCI card form factor, and providing that as a complete acceleration solution. So let's look a little deeper at the Speedster 7T. So Speedster 7T, again, is a standalone family of FPGAs. This is TSMC 7 nanometer process. And I mentioned that the two-dimensional NOC at 20 terabits per second is the foundation. So if I took a traditional FPGA and I said, okay, I'm going to put some Ethernet on there, I'm going to put a PCI Express, and I'm going to make a SmartNIC out of it. If I go back quite a few years, you have your FPGA fabric, and you would create circuitry, or RTL, that would route all the traffic from the incoming Ethernet packets. It would go through some type of packet processing, and then it would go to your PCI Express. Creating that logic in traditional FPGA logic is going to be expensive in area. It's going to be expensive in power. What the 2D NOC is, it's like a superhighway. It's a hardened piece of IP. It's super fast. It's deterministic. And it connects all of the external I/O, that means the memory interfaces, the PCI Express, the Ethernet, and gives it a way to route to each other as well as to the functional blocks like the machine learning processors on board or other functional blocks that have been put in by the user. And the bandwidth of it is such that it exceeds any of the external inputs. So what you don't get on the inside of the FPGA are bottlenecks. You're pretty much boundless on the inside. And a user's application can be set up in such a way as to be deterministic, which is very critical for a lot of these edge compute applications.
So, Tom, that was a great overview of the Speedster 7T, but can you tell me more about SpeedCore?
Yes. So Speedster 7T family of FPGAs. FPGAs are great for certain applications. A lot of heavy packet processing applications. If I look at appliances, so this could be security appliances, packet processing appliances, packet capture appliances, in quite a few cases, smart NICs, but smart NICs in the data center that are front ending a lot of the servers. Those are all use cases with your Speedster 7T. SpeedCore is taking the technology that we have in the FPGA. Primarily, it's the FPGA logic, it's the memory, it's the DSP engines, the MLPs, and parts of the network on chip, and making that available to a customer who needs some flexibility around certain portions of blocks that we offer, but they know that a large percentage of their application, it's a given. They don't need the flexibility. So they can bury that into an ASIC. So if I take this IP and marry it up with someone's ASIC design, they take a portion of their overall chip and they make it flexible using our technology. We are the only vendor that does that for high-end FPGAs. Our other two nearest competitors don't offer that option. So that could be useful in a 5G infrastructure. That could be useful in autonomous vehicles. We already have design wins in autonomous vehicles where they're going to put that little bit of flexibility down in with an ASIC, and now you're talking about a very high volume number of units. That's where SpeedCore comes in. The best thing about this is Speedster and SpeedCore use all the same design tools. I can actually take Speedster, or I can actually take the vector path card, which uses Speedster, and I can do prototyping, I can do field trials, I could do my early development of my high volume application, and then I could take just the pieces I need, embed it with my ASIC or my system on a chip, and now I've got the best of both worlds.
I see. So, Tom, you have Speedster 7T FPGA chips and SpeedCore IP. What about the accelerator cards you mentioned earlier?
Yes, so those are named Vector Path Accelerator cards. This is a partnership with Bitware, now owned by Molex. And they developed this card together with us. It's available from both companies. And what they've developed is additional software tools for use with the card itself. So that includes board management, that includes the Linux and Windows operating systems, and the toolkit that you need to develop on the card itself. So that again is available from us and from them, and it's a partnership that we did together.
Okay, so Tom, what other tools does Achronix provide to ease development?
We have the Achronix tool suite. So starting at the top is our ACE tool. This does the place and route. It does configuration of the FPGA itself. So once you actually have your bit stream, it optimizes where the code is going to go on the FPGA itself, does all the place and route, and actually provides the bit stream to put the firmware down onto the FPGA. Simplify Pro, that's actually a product that we licensed from Synopsys. And Simplify Pro, this version of it comes from us, is supported by us, and it's optimized for our FPGAs. And then for simulation, we support multiple tools, including VCS, QuestaSim, Incisive, and Riviera. So those are all supported by us. Those are third-party solutions. And there are multiple partnerships that we're starting to evolve with HLS providers. And again, this whole tool set supports Speedster, SpeedCore, and Vector Path.
All right. So, Tom, can you recap your main points for me?
Sure. So, data explosion. We're looking at exponential data growth around the world. Every business around the world is going through this digital transformation, and there's so much data that our traditional infrastructure of core data centers is not sufficient to manage and process all this data. So we pushed a lot of the core data center applications out to the edge. You've got edge compute, we have 5G, we have this different technology where we pushed everything out to the edge. And then on top of that, there's this exponential growth in data accelerator technology. And that comes in the form of GPUs, of FPGAs, and ASICs. Achronix is an FPGA company. We cover more bases, we cover more workloads. We feel that the FPGA is the perfect fit for data acceleration across many different workloads. And then we're the only high-end FPGA company that offers the fastest FPGA in the world, offers intellectual property, so you can take portions of the FPGA and embed that in your own solution. And then, of course, we have the vector path acceleration cards as well. And all of that is under one tool chain.
Excellent. So, Tom, if my audience wants more information, where should they go?
So go to achronix.com, and under technical support and getting started, you can go visit there. What you'll do is you'll register online, and you can get free evaluation licenses for the Achronix design tools and get started. We work with ecosystem partners every day, and I'd say at least once a week, once every 2 weeks, we're bringing on another partner. They take their solution and they map it into our platform, and that's the first step of getting started with implementing their designs with FPGAs.
Excellent. Well, Tom, I think that's all I have time for today. Thank you so much for joining me.
Thank you for the opportunity, and we'll see you soon.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Achronix. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.